If the chemical composition of a propellant charge changes, the tactical visibility of a 10,000-ton cruiser changes with it. On July 6, 1943, the light cruiser Helena lost her cloak of darkness not because of a tactical error, but because of a logistical boundary. When the supply of flashless powder ran dry, the ship transformed from an invisible predator into a strobing beacon off the north coast of Kolombangara Island, at the mouth of Kula Gulf. The United States Navy fought a specific kind of war in the Solomon Islands. It was a war of geometry and darkness, fought within the narrow confines of New Georgia Sound. In this environment, the ability to see without being seen was the primary survival constraint. USS Helena, a St. Louis-class light cruiser, excelled at this calculus. She carried 15 6-inch guns mounted in 5 triple turrets, a battery capable of delivering a volume of fire so dense she earned the nickname the machine gun cruiser. But this mechanical output relied on a chemical prerequisite. To fight at night, a ship required flashless powder. Standard smokeless powder, despite the name, produced a massive release of thermal energy and visible light at the muzzle. This expanding gas created a blinding white flash that ruined the night vision of the ship's own lookouts and optical fire directors. More dangerously, it provided a distinct aim point for enemy optical sensors. Flashless powder incorporated cooling agents and inhibitors into the nitrocellulose matrix to suppress this secondary ignition. It was a finite resource stored in the magazines alongside standard charges. On the night of the engagement, Helena expended her allowance. The decision to continue rapid fire with standard charges forced a trade-off between offensive output and defensive concealment. The moment the gun crews switched to standard charges, the darkness broke. Each salvo of 15 guns created a continuous sheet of flame along the hull. In the humid air of the Solomons, this light did not dissipate. It hung around the ship, illuminating her profile against the black water. The Imperial Japanese Navy response was governed by their own doctrine of night combat. They relied on heavy torpedo armament and excellent optical lookouts. The illumination provided by Helena's own guns gave the Japanese destroyers a perfect targeting solution. They did not need radar. They simply aimed for the center of the flashing light. Helena was struck by 3 Japanese torpedoes in roughly 3 minutes. The physics of a long lance impact are catastrophic. The warhead carries over 1,000 pounds of high explosive designed to break the keel of a capital ship through the expansion of gas and the shockwave of the water hammer. At about 02:03, a torpedo struck near frame 32 on the port bow. The structural continuity of the forward section failed immediately. The bow sheared off completely, detaching from the rest of the hull. A second torpedo struck near frame 82 and a third struck near frame 85 at about 02:06. These impacts destroyed the watertight integrity of the engineering spaces and snapped the structural spine of the ship. The keel failed, the hull slowly jackknifed, hinging at about frame 82. The center section, weighed down by flooding in the heavy machinery spaces, pulled the stern and the severed forward bulkhead toward each other. The buoyancy distribution was destroyed in seconds. The loss was not a slow decline. She broke up and sank within about 20 minutes after the third hit. While the bow section remained buoyant due to intact compartments, the main body of the cruiser plunged toward the seabed. About 168 crewmen are commonly reported lost. The Bureau of Ships report states that of 1,188 people aboard, fewer than 200 were lost. The ocean closed over the site and the tactical grid moved on. The wreck fell into the deep, entering a zone where the laws of surface combat are replaced by the laws of hydrostatic pressure and sedimentation. For 75 years, the specific resting place of Helena remained a data point on a map, but the physical reality of the wreck was unknown. This documentary is not a story of recovery. The United States Navy classifies this site as a war grave. There is no salvage operation to raise the steel. There is no gold to recover. The objective is forensic. To understand what happened after the hull slipped beneath the surface, we must look at the environment that received it. The deep ocean is not a void. It is a hostile, high-pressure environment that preserves evidence even as it crushes structure. Finding the machine gun cruiser required modern technology to pierce the same darkness that hid her in 1943. The question is not just where she landed, but in what condition the physics of the descent left her. 2,821 feet. This is the vertical distance separating the surface of New Georgia Sound from the resting place of the hull. At this depth, the environment is defined by the physics of hydrostatic pressure. This force is the weight of the water column acting on every square inch of a submerged object. For every 33 feet of depth, the pressure increases by 1 atmosphere. By the time the hull of Helena reached the bottom, it was subjected to a crushing load of over 1,200 pounds per square inch. This force is constant, omnidirectional, and merciless to any sealed volume. Unlike the transient violence of the blinding muzzle flash that marked her loss on the surface, hydrostatic pressure does not fluctuate. It tests the yield strength of bulkheads and hatch seals. If a compartment remains watertight during the descent, the pressure differential between the air inside and the ocean outside becomes extreme. Steel plates designed to deflect 6-inch shells can buckle inward if the pressure equalization fails. The ocean forces its way into every void, compressing trapped air and imploding sealed instruments. The structure subjected to this crushing test was a complex industrial machine. Helena was built around a specific engineering philosophy known as the unit system. In older cruiser designs, the boiler rooms were grouped together, followed by the engine rooms. This saved weight, but created a vulnerability. A single hit could knock out all steam production. Helena utilized an alternating arrangement. A boiler room was followed by an engine room, then another boiler room, and another engine room. This unit system layout was designed to preserve propulsion if a torpedo struck a single compartment. It allowed her 100,000 shaft horsepower plant to maintain output even after taking damage. However, during the sinking, this complex internal subdivision likely created a chaotic flooding sequence. As the ship broke apart and fell, the heavy machinery spaces flooded at different rates, altering the center of gravity and the angle of the descent. The fall through the water column stripped the wreck of its lighter components. Hydrodynamic drag acted on the superstructure, tearing away antennas, canvas awnings, and rigging. The heavy armored belt and the triple gun turrets acted as ballast, pulling the hull into a stable orientation. The wreck did not tumble randomly. The physics of buoyancy and drag aligned it as it fell toward the substrate. The bottom of New Georgia Sound is not a clean concrete floor. It is composed of deep volcanic silt. This sediment is soft, easily disturbed, and rich in iron. When the 10,000-ton displacement of the cruiser impacted the seabed, it did not stop instantly. The keel plowed into the mud, burying the lower hull sections. The impact energy transferred into the sediment, triggering a turbidity current. A massive cloud of silt would have risen around the wreck, bearing the evidence of the impact crater. For a salvage or survey team, this terrain creates a difficult noise-to-signal ratio. The volcanic rock scatters sonar waves, and the iron content can interfere with magnetic anomaly detectors. The wreck is hidden not just by the darkness of the depth, but by the geology of the trench itself. Finding the ship requires more than just dropping a camera. It requires a systematic acoustic sweep of a chaotic volcanic floor. The search team must distinguish between a geological formation and the sharp, unnatural angles of manufactured steel. It took 75 years for the operational timeline of USS Helena to resume. The gap between her loss in 1943 and her reacquisition in early 2018 was not due to a lack of interest, but a lack of access. The depth of the Solomon Islands prohibits casual exploration. It requires a dedicated platform capable of sustaining operations in deep water. In March of 2018, the research vessel Petrel arrived in New Georgia Sound. The mission was not a treasure hunt. It was a systematic survey designed to convert historical coordinates into verified physical locations. The primary tool for this localization phase was side-scan sonar. This technology solves the problem of optical visibility by ignoring light entirely. A side-scan sonar system consists of a towfish, a sensor package towed behind the surface vessel on a long cable. As the ship moves along a pre-planned grid, the towfish emits fan-shaped pulses of acoustic energy toward the seabed. When these sound waves strike the soft sediment of the volcanic floor, they are largely absorbed or scattered. When they strike a hard, manufactured object like a steel hull, they reflect a strong signal back to the receiver. Crucially, the object also blocks sound from hitting the seabed behind it, creating an acoustic shadow. The analysts on the surface do not look for the ship directly, they look for the sharp, geometric shadow cast by the wreck against the noise of the seafloor. Once the sonar team identified a promising anomaly, the operation shifted from detection to identification. This required a different tool, the remotely operated vehicle, or ROV. The ROV is a robotic work-class submersible tethered to the mothership by an armored umbilical cable. This cable provides power and fiber optic data transmission, allowing a pilot on the surface to fly the vehicle with zero latency. The ROV is the only way to bypass the weight of the water column. It brings high-intensity lighting arrays and 4K cameras into an environment of absolute darkness. However, the operation is constrained by the physical reality of the tether. The pilot must manage the cable tension and the current drag to prevent the vehicle from becoming entangled in the wreck. This is a look but don't touch environment. The ROV hovers, documents, and moves on. As the ROV descended toward the anomaly in April 2018, the chaotic geology of the seabed gave way to the orderly lines of naval architecture. The cameras revealed a debris field of scattered metal followed by the main hull. The steel was heavily encrusted with marine growth, but the preservation was remarkable. The low oxygen levels at this depth slow the rate of corrosion, leaving the ship in a state of suspended decay. The identification of the wreck was confirmed by a specific visual marker. On the starboard side of the stern, the hull number 50 was still visible. The white paint had faded, but the relief of the numbers remained distinct against the gray steel. This provided the definitive proof required to close the historical file. However, the survey revealed a strange biological detail amidst the industrial ruin. Perched directly on the stern near the identification number was a large, deep sea crab. This organism became an unplanned focal point of the initial footage. In a lifeless, high-pressure zone, the presence of the crab highlighted the contrast between the static, dead steel of the warship and the slow, persistent life of the trench. It stood as a biological sentinel on a manufactured tomb. The cameras panned across the deck, revealing the 20mm anti-aircraft guns still trained skyward and the main battery turrets rotated to port. The survey proved that the ship was upright. It verified the location. But the most important data lay in the structural breaks. The debris field was not random. It held the forensic signature of the final moments. The separation of the bow and the fracture amidships were not just historical footnotes. They were physical realities lying in the silt, waiting to be read. How does a continuous structural spine fail when the hull is still partially buoyant? The answer lies in the limit of longitudinal strength when the distribution of weight is violently altered. The survey of the USS Helena wreck site is not just a visual tour, it is a forensic confirmation of a specific catastrophic failure mode known as the jackknife. The evidence on the seabed confirms that the destruction of the cruiser occurred in two distinct phases, driven by 3 torpedo impacts. The first piece of the puzzle is the forward break. The initial torpedo struck the starboard side at frame 32. In naval architecture, frames are the transverse ribs of the ship, numbered from bow to stern. Frame 32 is located forward of the number 1 turret. The damage here was absolute. The explosion severed the structural connections holding the bow to the rest of the chassis. The survey footage reveals a clean separation, confirming that the bow did not crumple or tear slowly, it was sheared off. This created a standalone vessel, a floating section of steel that was no longer connected to the heavy machinery of the main hull. The second phase of destruction provides the primary evidence of the jackknife failure. 2 torpedoes struck the ship amidships, flooding the engineering spaces. This created a massive localized weight at the center of the ship. However, the stern section remained watertight and buoyant. This created a lethal disparity in the load path. The center of the ship wanted to sink immediately, while the stern wanted to remain on the surface. The keel, the structural backbone of the ship, could not withstand this opposing torque. The ship bent in the middle, acting like a giant hinge. The steel plates of the deck came under extreme tension, while the keel plates faced extreme compression. The metal reached its yield point and snapped. This is the jackknife. The ship folded, destroying the structural integrity of the hull girder. The remotely operated vehicle, the camera in the dark, documented the result of this physics equation. The main wreck consists of the center and stern sections, but the break area is a tangled mass of torn steel. The deck plating is ripped upward, consistent with the tension failure of the jackknife action. The engineering spaces are exposed, revealing the boilers and turbines that were the heart of the unit system. This debris field tells a story of rapid disintegration. When the keel snapped, the structural stability of the entire vessel vanished. The heavy center section dragged the stern down with it, pulling the aft hull vertical before it slipped beneath the waves. The violence of this break explains why the debris field is scattered. It was not a controlled descent, it was a structural collapse followed by a ballistic fall to the bottom. The survey data aligns perfectly with the historical accounts of the survivors. They reported the ship buckling and the stern rising into the air. The twisted metal on the ocean floor validates those observations. The wreck is not just a ship that sank, it is a ship that broke its back. The separation of the bow at frame 32 and the jackknife fracture amidships created a wreck site defined by fragmentation. However, this fragmentation created a unique anomaly. The main hull and the stern sit together in the darkness of the trench, verified by the sonar and the ROV. But the bow section, severed at frame 32, is not immediately adjacent to the rest of the wreckage. Its absence from the main debris field points to a different timeline of sinking, one that introduces a variable of drift and duration that the main hull did not experience. If a sinking vessel maintains its transverse stability while losing longitudinal buoyancy, it acts as a self-righting mechanism during the descent. The main wreck of USS Helena sits perfectly upright on the seabed, its keel buried in the silt and its guns trained to port. This attitude suggests that after the broken spine separated the stern from the bow, the main section fell in a stable, heavy orientation, guided by the ballast of its armor and machinery. The survey reveals a distinct separation between the main wreckage and the bow section. This distance is not merely a result of the debris field scattering, it is the physical evidence of a temporal anomaly. While the center section and stern sank within minutes of the structural failure, the bow section did not. The forward compartments, severed cleanly at frame 32, remained watertight. The bow remained afloat, drifting in the current of Kula Gulf until the afternoon of July 7th. This buoyancy allowed a number of survivors to use the floating steel island as a life raft before it finally succumbed to slow flooding. The force required to create such a clean separation was generated by the chemistry of the Type 93 torpedo warhead. This weapon was distinct from its American or British counterparts due to its propulsion system and its explosive payload. The Type 93 utilized pure compressed oxygen rather than compressed air, allowing for a larger warhead without sacrificing range. When this warhead detonated against the hull, it did not rely solely on shrapnel to destroy the target. The explosion converted a massive charge of high explosive into a rapidly expanding gas bubble. This bubble expanded faster than the surrounding water could compress, creating a void. When the bubble collapsed, the water rushed back in at supersonic speeds, creating a shockwave known as the water hammer. This hydraulic impact, combined with the gas expansion, delivered a shearing force capable of cutting through the double bottom and vertical keel of a light cruiser in milliseconds. The violence of this separation stands in contrast to the evidence found on the main hull. The remotely operated vehicle identified a specific detail on the anti-aircraft decks that speaks to the velocity of the sinking. A shield for a 20mm Oerlikon gun was found bent backward, folded down against the deck. This deformation was not caused by the torpedo explosion, which occurred below the waterline. It was caused by hydrodynamic drag. As the main hull plummeted 2,821 feet to the bottom, the water resistance against the flat surface of the gun shield became great enough to bend the steel. This indicates a rapid terminal velocity descent. The ship did not glide when it fell. The heavy armor belt and the flooded machinery spaces pulled it down through the water column with immense energy. The confirmation of these details brings the survey to its operational conclusion. The cameras have located the hull number 50 on the stern. They have documented the jackknife fracture that broke the ship's spine. They have mapped the separation of the bow. The objectives of the mission, identification, and forensic documentation are achieved. There is no engineering justification for recovery. The depth of the water makes a lift operation technically prohibitive, requiring a massive expenditure of resources to recover corroded steel. More importantly, the site is defined by its legal and ethical status. The wreck is not abandoned property. It is a sovereign vessel of the United States Navy. The survey team observes the geometry of the wreck, verifies the history, and prepares to leave the site exactly as they found it. The decision is not to touch, but to witness. The visual confirmation of the number 50 on the stern plate is the final data point in the forensic file. This integer, embossed in steel and preserved by the anaerobic conditions of the deep trench, converts a historical probability into a verified coordinate. The survey of USS Helena is complete. The transition from a lost ship to a discovered wreck alters the legal status of the site. The United States Navy maintains a specific policy regarding its sunken vessels. This is the Wargrave Protocol. Under international maritime law and the Sunken Military Craft Act, the wreck of Helena remains the sovereign property of the United States. It is not abandoned. It is not subject to salvage law. The site is protected by a policy of non-disturbance. This protocol is not merely symbolic, it is a rigid legal boundary that prohibits the removal of artifacts, the penetration of the hull, or any physical interaction that disturbs the sediment. The remotely operated vehicle observes the site, maps the debris field, and leaves. The acoustic shadow cast by the hull on the sonar screen remains the only imprint the survey team takes with them. There is no recovery of bells, brass plates, or personal effects. The reason for this strict boundary is the human cost associated with the coordinates. When the ship jackknifed and fell into the trench, she took 168 men with her. These sailors remain on patrol. The site is their final station. However, the loss of the ship was not a total annihilation of the crew. 735 men survived the sinking. They survived because of the discipline maintained during the abandonment and the buoyant stability of the severed bow section that refused to sink immediately. The legacy of the ship, however, is defined by more than just her loss. It is defined by the technical proficiency that earned her a unique designation in the fleet. Helena was known as the machine gun cruiser. This nickname was not hyperbole. It was a recognition of a specific operational capability. Her gun crews and fire control parties achieved a rate of fire from her 6-inch battery that created a continuous stream of ordnance. In the battles leading up to her loss, this rate of fire was so intense that Japanese observers often misidentified the cruiser as a battleship or a new type of automatic weapon platform. This capability was not a function of magic. It was the result of drilling the loading cycle until the mechanical limits of the hoists were reached. The wreck on the bottom represents the physical machine that enabled this output, now silent and covered in silt. The discovery of the wreck in 2018 closed the loop on a 75-year-old question. The survey provided the families of the lost with a specific location. It confirmed the violent physics of the torpedo impacts and the structural failure of the keel. It verified the history written in the after-action reports. The ocean floor is a repository of evidence. In the high-pressure darkness of New Georgia Sound, the steel of the machine gun cruiser remains intact. The guns are trained to port, locked in their final firing solution. The hull number 50 is visible to the camera. The survey team retrieves the robot, winds in the tether, and sails away. The site remains a protected sovereign territory, a war grave that will not be disturbed. The history is secured and the ship is left to the deep.